Good evening, everyone. Welcome to tonight's webinar for the Classpad.net. We'll be discussing function transformations, connecting geometry to algebraic reasoning with Classpad.net. For the sake of webinar quality, everyone is automatically muted and all videos are turned off. If you do have a question, you can type it in the chat panel and I will respond back to the group or ask our presenter, Dr. Karen Greenhouse, to respond to the entire group. Before we begin, I just wanted to introduce ourselves a little bit. My name is Amy Chow and I'm the National Training and Product Manager with Casio's Education Division. I'm currently have been a math educator for the last 14 years. And tonight we have Dr. Karen Greenhouse presenting for us. And I'll let her introduce herself.
Hello, thanks for joining us. And I'm Karen Greenhouse. I know I recognize several of you, so you might be tired of me introducing myself. So just math educator forever, it seems. I work with Casio. I teach at Drexel University. And I'm really kind of dedicated to using technology in mathematics. So that's what this Classpad.net allows me to use. If you're distance teaching right now, this is a great tool for helping students visualize mathematics. So that is what I'm using is Classpad.net. If you look in the chat panel, if you've never used Classpad.net and you want to play along, it is a free tool. And I'm going to actually click on the website. If you take that link, it takes you right to this page. And if you just want to play along, kind of do what I'm doing or your own shape, we have plenty of time to kind of go through that. So just hit start exploring and it lets you open a page to just play with. If you have an account, certainly feel free to open your account and then you can save what you're doing. That's the main difference for those of you not familiar with Classpad.net. It is free. You don't have to have an account. You can just start exploring. So that's why it's a really nice tool to use with students. If you're in a Zoom environment or an online environment, you can actually say, hey, everyone open up a Classpad.net. They don't have to have an account, but they can do calculations and geometry and statistics right there with you on the screen. But then if they do create an account, also free, they can save what they've done. So that's the main difference. If you just explore, it's not going to save because it doesn't know where to save it, but you can still do all the math. But if you create an account, then everything you do is saved. So I'm going to actually log into my own account just because I like to save the things I do, and I will probably share it with you later. Just takes a second. So I'm going to log in, and if you're just using the playing account right now, the one main thing that you'll notice that's different in the guest account where you're just kind of playing and you're not going to be able to save, you don't have this little cloud up here. I'm in my account, and because I'm in my account, it's auto saving. So that's a really nice feature of Classpad. I don't have to forget to save and then lose something. It's always saving I don't know how many, every couple of seconds, I think it's saving if you do anything. So I'm in my account. Yeah. Can you not see that?
The screen hasn't changed yet. Can you? Nope.
What has? Oh, did I stop sharing? No. So
no, we can still see the PowerPoint.
Well, that's bizarre. Hold on. Sorry. There we go. So should I go back and show what I was talking about?
Yes, that probably be
all
good.
right. So let me back up. Sorry, I was going so fast. Didn't realize the screen wasn't changing. So this is the landing page. That's the link that I sent you. And if you're working with students in a remote environment and you want them to do some interesting math, like draw a picture or do some data collection or do a calculation, if they just hit start exploring, they can start using this tool right away. No account needed. If you want to save anything that you create, that's why you would have an account, because then it saves. So I've already logged into my account. And the main difference for those of you who are just kind of playing along in the non-account thing is this cloud up here to the right. That means when you're in your account, everything I do is auto saving. So I never have to remember to save. It's going to do it automatically. So today's focus is really about how important prior knowledge is to helping students understand new concepts. So I'm really trying to connect prior knowledge of geometry to algebraic understanding of functions and transformations. So one thing students start, I looked this up and I'm using the Common Core standards as sort of my basis just because so many states use some form of the Common Core. And so let me just look at my notes here, make sure I got this right. So it's about in 7th grade when it's like students have done geometry since 1st grade where they've learned about shapes and attributes. But in 7th grade is where they first get introduced to a type of transformation, the dilation. So they're really focusing on scale. So it starts in 7th grade. So that's sort of a beginning understanding. And then 8th grade is sort of the powerhouse year for geometry and understanding transformations. That's where they really explore all the properties of reflection and rotation and transformation, not translations, and dilations, where they're really looking at what happens to a shape when it is translated, what happens when it's rotated. And then we're going to look at it in a coordinate grid. So that's happening in 8th grade. And they don't get to function transformations until algebra 2, really. And that's a long gap. But if you are continually referring back to this prior knowledge of geometry transformations, that can really aid in students understanding function transformations. So I'm just going to start from a geometry basis. So in Classpad.net, I can do whatever math I want simply by clicking somewhere on the screen. So I'm going to just click, and here's all the things that I can do. And that's why this is such a great tool to use with students, because you can do anything. I could do a calculation, or I could say, hey, everyone open a graph, make a graph of this. Open the geometry, draw a picture. So there's everything you can do is in this one spot. And so I'm going to open a geometry. So those of you playing along, you just click the geometry and it opens up this geometry window. And these are what we call stickies, and they can move wherever I need them to. So that's a really nice feature of Classpad.net. You have unlimited space, and you can basically create lots and lots of different math all in one place. So I'm going to be looking at geometry, and this is the standard geometry thing. Down here are all my construction tools, my straight edge tools, like segment, line, ray, vector, circles and arcs, and here's polygon, rigid polygon. So lots of things here. And over here to the right are all the things I can do once I have something in my screen. So it's a full geometry program. So let's go back to 7th grade. So in 7th grade, they are really focused on dilations. And then in 8th grade, they really get introduced to all the different types of transformations. So first, it's just, can you describe what's happening in the transformations? And so what I like to just kind of refer back to a simple way to start with students when we're thinking about transformations is to get a shape. And I'm going to use the polygon tool. And there's 2 different polygon tools. And one is just a polygon and it will change. And one is what we call a rigid polygon. I'll show you the difference right now. So if I use the regular polygon tool and make a shape, so let's just make a quadrilateral. That's with the regular polygon tool. And that means it's a generic, in this case, quadrilateral. And I can move the vertices and change it to any other quadrilateral, right? If I use the other polygon tool, so you'll see the difference. This is your regular polygon and this is a rigid polygon. So it is then confined. So let me just show you what I mean. So let's make another quadrilateral. So you'll see it starts off exactly the same, except when I close it, you'll notice 2 of the vertices disappeared in the rigid. And that's because this is rigid and this one cannot be changed. All it can do is turn or slide. It is a rigid. So depending on what you're doing with students, this you would use either one. If you don't want them to change the shape they first drew, you would use rigid. And I'm going to use rigid. So I'm going to get rid of this one here by selecting it and then just hitting my delete button. Well, okay, that did not work. I must have selected more. So when all else fails, start again. Let's just make another. So what I want everyone to do, if you're playing along with me, is use the rigid tool and just make any polygon. I don't care how many sides it has. It doesn't really matter. Just make a polygon somewhere on your geometry screen if you're playing along with me. Select the arrow tool. This is our selector. This allows us to move things, construct things, those types of functions. So I have this shape, and when students are first exploring transformations in geometry, first they're just kind of looking at objects and moving objects, and sometimes it's physical, sometimes it might be with patty paper. So an easy way for students to kind of get an understanding of what each transformation does is just to move things. So I'm going to move things on my screen. So if I click in here, notice that I can move my shape. And because it's that rigid one, it's not going to change, which is what I want. I'm talking about rigid transformations. So if I were to ask students, what do you notice? What's happening? Here's my original shape. And now I've moved it. What happened to the shape? So in the chat panel, if you think of being a student, what did you notice? So what am I doing as I move this shape? What's happening to it compared to its original position? If anyone wants to respond. And if not, I will respond for you. So hopefully students are saying, oh, it's sliding. Okay, so that's a really nice description of it's sliding. And then excellent, Tom, it's staying the same size. Nothing about the shape changed, right? It's still got the same number of sides. It's still got the same shape. All I did was move it to a different location and I slid it. And so this is where you might say, well, this is called the sliding, the moving of a shape left to right, up, down, diagonal is called a translation. So then that's where you start getting into, what happened. It moved, it slid. That's a translation. The object itself did not change in any way except its position. And this is why I like to use the rigid polygon tool, because now I want to talk about, say, rotation. So now I can say, okay, now look at the shape. Here's my shape. And now, let's make sure I'm doing the right. What's happening to it in this case, right? So is it moving the same as it was in the translation? What is happening here? And hopefully they're going to say it's turning, and I can turn to the left and I can turn to the right, and I'm turning around a specific point. And thank you very much, Amy. It's rotating around a point I could have a point out here. But the idea is that you're showing students that both of these are moving the location of the original shape, but they're not changing the shape itself, right? So this is another type of a rigid transformation. I'm turning. So we have sliding or translation. We have turning or rotation, always important to do the precise mathematical words. And then watch what's happening now. And just so you guys know what I'm doing, I don't want to get into official, how do you construct a dilation? I'm just using my mouse and I'm in the screen of the geometry. And so if I roll my mouse one direction, what's happening to my shape? Anyone? And I move it the other. So all I'm doing is basically zooming in and out, right? It's getting smaller or it's getting bigger, right? So is the shape changing location? No, it's not changing location, but it is changing size. So that's different. So now you would compare this to the rotation and the translation. Those didn't change size, but they changed location. Those were called rigid. This one's actually changing its size. The sides seem to get smaller or they get really big. So this is what we call a dilation, which is not a rigid transformation because it changes the shape itself. So again, we're just having discovery. So this is happening in the beginning of geometry in 8th grade. They're learning about what these things are. The only one that I have a hard time with where I can't just make the shape flip over because it's very hard to do in a geometry software. You have to actually construct a flipping over a mirror. So if you were using this with students, when I first did it, we used to have, I don't know if anyone remembers the red, I think they were called Myras, where you could actually see the reflection and then you talk about reflections. But in geometry software, I do actually have to create a mirror line. So I talk about that with students. This is a mirror line. And the last transformation we're going to talk about is, and so when I do this with the geometry software, you have to construct something to reflect over. It could be one of the sides, but I like to make sure it's outside of the shape. Then you select the shape and you go to construct, and you'll see here's all my transformations, which we're going to talk about in a little bit. But I'm going to now show the last type of rigid transformation. And then it's asking me, whoops, sorry. It's asking me to, oh, I did it wrong. Sorry, I moved my window before I actually did what I was supposed to. So construct, reflection. Notice up here, it gives you little hints of what you're supposed to do next. So select a line. So that's my mirror line. And then it's going to reflect it. So now we can talk about, what do you notice? Well, it looks like it flipped over the line, right? And What's different about it? Well, this time it looks like the points are in the opposite direction. So there's a lot of different ways you can explore those properties. So these are very quick and informal types of introductions to reflections. And then in 8th grade, they move on and they really get into the properties and, what happens to the points. So this was just a brief kind of how could you introduce students to reflections. So this is 8th grade, beginning of 8th grade. And now I'm going to kind of scroll down my paper and I'm going to open another geometry sticky. So this is the nice thing about Classpad. You can pretty much open as many stickies as you want. So I'm going to open up a new one. And this time I'm going to now go into the next step, which would be actually looking at what happens when we have our transformations, our rigid transformations, and what happens to the coordinates and the points, because that's what we're going to then take as our prior knowledge and connect to algebraic function transformations. So here I am in geometry again, and I'm going to show you in the process of doing this how you can add a grid to a geometry sticky. So every sticky in Classpad has these 3 dots up next to it, and that's where the settings for the individual sticky are. So each sticky is basically its own separate window, if you want to think about that. So if I go up here, you'll notice in geometry, you have 3 different types of grids, basically. Or it's really 4 if you count the diagonal. So a regular grid, this is a dot grid, this is an isometric grid, which is great for 3D. And so I want to turn a grid on. So notice that just a checkbox. So I'm going to turn on a grid. And since I'm working with coordinates, I also want to turn on the axes. So notice it's just a checkbox, and I can choose to show the numbers, which I do want to do. And notice you can set up a window. I'm not going to deal with that right now, but you can turn on the X and Y, set up your window, scale, all the types of things. Down here is kind of a nice feature when you have a grid on and you're working with shapes, and especially when you're introducing things with students where you really want them to discover the connections. So you may not want them having coordinate points that are decimal values, right? So this is where snap and fixed come into play. So snap will automatically kind of force a point to land on a nice part of the grid and not be a decimal. And that's a nice feature to have on so that your shapes work out well. Fixed does the same thing, but snap you can kind of have a little flexibility. Fixed like pushes it right onto one. So I tend to use snap unless I'm working in the 3D. So I'm going to turn on snap. I'm not going to do anything with this. Labeling is important in our transformation, so I'm going to let it stay on. And I am going to change my decimal values since it's going to snap to a complete decimal, a nice grid intersection, basically. I'm going to just keep it at 1. Yeah, I probably could keep it at 0. So once I decide how I want my settings, now I hit OK. So that is something you can do in every single sticky that is in Classpad.net. Change the settings for that specific sticky. And we'll see that again when we get into graphing. So here's my geometry window, but now it looks like a graphing, a coordinate grid. And I'm going to zoom in just so I can see a couple more numbers in here. I could also expand my window a bit. So let's just, no, I like it like that. All right. So now I am going to just construct a polygon somewhere on this grid. And it doesn't matter what quadrant it is. We're going to be reflecting it over the x-axis, the y-axis. And here is something I'm just going to give you a heads up here. Unfortunately, in the geometry sticky, they don't allow you to select the axes as a line of reflection. They're working on that. They're working on making that change. But my workaround is to come over here and choose black as my color and basically go to the line tool, which is right here, and kind of put a line on top of the axes. So if I do that, and remember I have snap point, so it's going to snap to that nice point. And so you see my line, and I'm just going to snap it to another point. So now I have a line that is on top of the axes, but now I can use that line to be a reflection point eventually. So I'm going to do the same thing for my x-axis. And now here comes a feature. Those of you who are new to Classpad, maybe you don't know this. I don't want them to accidentally move this line, right? I want it to be the axis, and I don't want to necessarily see these points. So in this, you can select. So I'm going to select these 4 points that I really don't want to see. And if you go up to the arrow here, you'll see this word that says visible. And so whatever I have selected, I can now choose to turn it off. So I'm going to turn it off. And those points now, they still exist, but I've just hidden them. And then they could probably move the line if I'm not careful. So I'm going to select the lines. And you'll notice under visible, there's this word called lock. And if I hit lock, those lines cannot be moved even accidentally by the students. So I tend to do this when I know I'm going to be working in geometry and I am doing reflections and transformations and things around the axes. I kind of want to put that axis ability to reflect over them on there. So until they let me actually choose the axes, that's coming eventually, but right now that's my workaround. All right, so I have the axes that I can now select as lines of reflection. So what I'm going to do is I'm going to kind of show you what would happen in geometry and then how that can connect to algebraic function transformations. So in geometry, what they learn, so let's just make a polygon. So those of you working with me, I'm going to use the regular polygon tool this time. I think I will change the color to be blue. And just make a shape. It doesn't really quite matter where you make your shape, but just make some shape. Could be a triangle. I'm going to make a polygon. All right, so there's a polygon. And I'm going to be practicing reflection right now, right? Reflect over the X, reflect over the Y, and we're going to watch what happens to my coordinates. So in theory, I could measure all the coordinates of every one of these points, but that gets really cluttered. And so you really only need one vertices coordinate. So just pick a vertex, if you're doing this with me, on your shape. And so I'm going to select. So notice I'm in my arrow tool. I select one of my vertices. I'm going to go to measurement, and I'm going to measure that vertices coordinates. So G is at 8 and 4. X is 8, Y is 4. Now I'm going to reflect this shape over the y-axis, and I'm going to measure the coordinates of the reflection. So I like to use color with students. It's a really nice visual so they can kind of follow what's happening. So I'm going to change my color first. So let's make the reflected shape be red. And so to do reflections or any transformations, you select the object that you want to transform. You do that first. You go up here and you choose construct. And here's your choices. And we're going to reflect. So notice it says select what you're going to reflect over. So let's reflect over the y-axis first. So when I click that, it's going to show me the reflection. And here's what I really love about when we do these transformations. The pre-image has the original points, right? E, F, G, H. And the image, after you've done your transformation, automatically puts those primes in there so that you know that this is a copy of the original, which I really love that. And if I were to then do something with this one, it would have double prime and triple prime, and you can do several. So here's what we're asking students to figure out. What happened? So we already know, let's say they've already discussed what they noticed happened with reflections. The objects flipped over that line, their orientation reversed direction, but now we're looking at the coordinates. So we want to measure the coordinates of G prime and see how it compares to the coordinates of G. So I selected that G prime. I'm going to measure and coordinates. All right, so it almost looks like they're exactly the same except for what? So what changed? If I was working with my students, what are they noticing happened when we reflected over Y? What happened to the coordinates of the point? Anyone? And I'm going to pull up a text sticky. So this is a nice thing too. I can write my notes right next to what I'm doing. Orientation switch. We knew that, but what happened to the coordinates of the point? So the original was 8, 4. And what is my new? I reflected over Y. So reflection over Y. What happens? The X, right? The X coordinate is now, I'm going to say it's inverse. So we happen to start with a positive. And the reason I'm saying inverse is because I could have started with a negative and reflect it over, and now it would be positive. So inverse kind of covers both cases, whether you started positive and it switched to the inverse of negative, or whether you started negative and it switched to the inverse of positive. The key here is that the x coordinate changed to its inverse, but the y coordinate did not. So if you were then to ask students, okay, well, what if we flip now over the x-axis? Do you think it's going to be the same? Is the same thing going to happen? So what do we think is going to happen if we reflect over the x-axis? I should put y-axis up here. Anyone want to make a conjecture before we do it? If I flip the original over the x instead of the y, so when I flipped over the y, or I'm sorry, reflected over the y, I got the inverse of the x value, x coordinate. And so Amy is suggesting that the y coordinate will become the inverse. All right, so that means we think it's going to become 8. The g prime there is going to be 8, -4. So let's test it out. And that's a nice thing about dynamic geometry. You can do it really quickly. So now we're going to select the shape. We're going to construct another reflection, but this time our line is going to be the y. And let's measure the coordinates of this new image. And let's see if Amy was right. And Amy was right. That's awesome. So if we reflect over the x-axis, we are going to get the y coordinate is now its inverse. Yay, Amy. So you could keep doing, you could put the line at x equals y and have it reflect over that, which is sort of reflecting over the origin. So lots of things you can do. We're going to come back to this. How does this then help you understand functions? But I wanted to move into, I kind of wanted to show you some of the geometry transformations first and what students would hopefully get from that, and then how that then transfers in. So let's look at, let's just do transformation. So I'm going to do the same thing. I'm going to turn on my grid. So I went to settings, numbers, snap, and we'll keep it at 1. Let's zoom in. And so, whoops. If you mess up, you can hit this little arrow here. That's edit undo, basically. And now I'm going to do another polygon. Let's try to make it be a different shape. So this time, let's make it be a triangle. And let's measure one of the original vertices. So I selected it. I go to measure. I hit coordinates. All right. So now we're going to just do, I'm just going to do 2 types of transformations because hopefully you're getting the idea. So here's this shape. Here's this point that's in -8, -4. How funny. I seem to like that number. Those digits, 8 and 4. But now I'm going to do a translation, which is a rule. So I'm going to do the same thing. It starts off exactly the same as you would with a reflection. I'm doing a transformation. I select the object that I want to transform, and I go to construct. Here are my choices. So notice I have 2 different types of translations, and I want to do a translation by coordinates because that's what I'm helping students understand how this works. So I'm going to translate using coordinates. But before I do that, let's say I tell the students I would like this shape. They hopefully already know that if I say I want to translate it, that it's going to slide up and down. So let's say I want them to tell me a rule, a way to slide this shape, transform it so that it ends up, right now it's in the 3rd quadrant, and I would like it to end up in the 1st quadrant. So what kind of rule? And this is nice to do with students because it can be any rule. They could all have different ones as long as the shape ends up somewhere in this 1st quadrant. So that's where we're going. And I'm going to ask you guys to give me a rule. So here's my shape, and I am going to construct a translation. And it's going to ask me, okay, where do you want X? How do you want to move the X coordinates, and how do you want to move the Y coordinates? So X, if we look at our axes, is going to move the shape left or right. And Y is going to move the shape up or down. So if somebody wants to make a conjecture on how we could move this left, right, and up, down to get into this 1st quadrant up here, how could I move this? Anyone? Come on. Amy's doing all the work here. All right, so we're going to do x is 10. And so it's positive, which means we're hoping that moves to the right. Okay, and now we've got y, and we'll use Tom's y of 9. So that means it should go up 9. Now, how do you know it's going to go right and up? Well, because our numbers are positive, and hopefully students have an understanding of integer movement and integer values. Positive moves you to the right if you're on the x, up if you're on the y. So where are we anticipating? It's going to go over 10 and up 9 is what we're thinking is going to happen. And let's see if that does. And I probably should have changed the color, but that's okay. All right, it did. Now, is it an actual translation? What did we learn about translation from way in the beginning? It slides my shape, but it doesn't change its size or anything like that. So let's measure the coordinates. And this is where you want them starting to make that connection of how does the rule that we just gave it, so we gave it a rule of move 10 to the right and move 9 up. How does this rule help us figure out where it landed? And so hopefully it's like, well, look, the original B was at -8, -4. How could you get to this new place using this rule? And you start making those connections. Maybe they start adding. They're like, oh, well, a -8 plus a +10 is a +2. Hopefully they're making that. So what they're seeing is that the translation rules add value or subtract value to the x and the y coordinates depending on the movement of the x and y translation. So that's where you're trying to connect them to. So I'm not going to keep going, but dilation, you can do all of these different types of transformations in geometry. They're learning all of this in 8th grade. So this is all prior knowledge in 8th grade. So hopefully when they get to you, if you're teaching, algebra 2, where you're starting to do function transformations, how can you pull out that prior knowledge to help them understand what's happening with functions and translations? So I'm going to scroll down, again, unlimited space. And this time I'm going to pull out a graph sticky. And we're going to start really simple. So here's a graph, and linear is usually an easy way to start. So I'm just going to give a linear equation. So if you're not familiar with this is a graph sticky. Right now it looks very much like the geometry sticky, but you'll notice it's a little different if I went to settings. So in the graphing, you can just turn the grid on or off, the axes on or off. You can't change the type of grid, but you can turn it off. You can change your windows. If you're plotting inequalities, you can do a union or an intersection. And you can, oops, didn't mean to do that. You can change how your coordinates appear. And standard means if they're a rational number, it's going to show up as a rational number. So I'm going to actually change so that I get a decimal value for right now. And I think I'm going to change my decimals to 1 again because I like that. But notice you can do conics and parametrics and those types of things. So I changed my settings. So down here at the bottom, you can enter a function, you can enter data, you can plot points, you can even add a picture. But right now, all I care about is we're just going to enter a function and explore how function transformations are related to geometry. So I'm just going to put a really simple linear equation in here just to start. So let's say it's 3x plus 2. And here's this function. And if you click it, anytime you graph anything in the graph sticky, when you click on the function itself, it'll bring up key points. So notice it's bringing me up the x and y intercepts, right? So what do I have students know? What do you notice? This 2 right here, maybe that connects to this 2. Hopefully they've already kind of understood that because we're at function transformation, so they should understand linear functions at this point. So if I said, I want you to reflect this function over the y-axis and write the new function for me and graph it, we're hoping, and this is where you want to pull in your prior knowledge, what do they know about reflections over the y? So let's scroll back up here. Reflections over the y was this situation right here. And what did we learn about the points? We learned that whatever the x value was, wherever you started, so if you started with -8, 4, when you reflected over the y, the x coordinate became its inverse number. So if I go back down here, and this is a bad point, we're going to pick a point. I'm just, notice all I did was select the line and pick a point. And now I have this point that I can move wherever I want on the graph. So I'm going to put it at a nice spot. There's a nice spot. And so if I remember from geometry that when I reflect over the y-axis, my x coordinates become their inverse number. If I reflect it, I know that there's a point on the new line, the line that is the reflection, is going to be negative 0.7, right? So here's where I might want to start collecting some data. So I'm not going to use the data point. I'm actually going to use the plot points because I know that I'm going to plot these points to help me figure out the equation. So notice that it's blue and this line's blue. So I probably want to change my color. So here's those 3 dots again. That means settings. So let's make it be red. Actually, let's make it be orange. I always pick red. We're going to go with orange. So I know that one point on this line, based on this right here, is going to be the reflection. So it's going to be a negative 0.7. And the y value is the same because I'm using my prior knowledge from geometry that when I reflect over the y, the x coordinate becomes its inverse. All right, so I could, well, let's look at this point. What would be the inverse of 0? Anyone? Hopefully students say, well, there is no inverse. It is just 0, right? And so that point, what have I just learned? They're going to have a point in common, which makes sense because we're reflecting. There are mirror images. There is going to be a point where they cross, right? And so now let's look at this point right here. If I'm going to reflect over, this point is going to have the x become its inverse value. So that means it's going to be a positive 0.7. And a 0. So all I'm doing, so notice as I do this, I chose to use the plot points. Did I do that right? Yes. Notice that points are showing up every time I enter it. So let's just do another 1 or 2. So I'm going to move this one way down here and find a point down here somewhere. There we go. Let's do one more point. So this point, if I reflect, the x becomes the inverse, and so that means it's going to be a positive 2.6, and a negative 6. All right, so what have students done? They have plotted points, so they know that the line they're looking for, these 4 points lie on it. So now if I ask them what is the equation of that line, and let's make it orange, there's lots of ways that they could figure this out. They could calculate the slope. And what do they already know about the intercept? If anyone hasn't figured that out yet, what do they already know about the intercept? Where is the intercept of this equation? Because it's linear and it's reflecting over the y. Yes, the intercept is right here. So we already know that. So they already know it's going to be +2. So the only thing that's changed is this right here. And so what we're trying to help them figure out is that a reflection of this function, how does that change basically the slope? And hopefully some of you have already figured out. But for students who maybe can't see it yet, we want them to try to figure it out. So they could do things like pull up the calculator and find the slope. And this is the nice thing. Notice that when you pull up the calculator, you get this nice keyboard here, soft keyboard, and it has all the templates that you might need. So I'm going to use this one to calculate my slope. So my slope, all I need to calculate my slope, so this should all be prior knowledge, is choose 2 points that I've plotted and do the difference of y over the difference of x. So let's choose the first 2. How about that? So if I do the difference of the y's, I'm going to have 2 minus the 4. So that's the difference of my y's. And then 0 minus, and notice it is a negative 0.7. So I'm going to put a parentheses around that just to clarify. And then when I hit execute, I should get the decimal value. And notice you have this standard to decimal. If you're in the guest version, you won't have the ability to toggle. That's another feature that's turned on once you have an account, but you still have the decimal, but I'm going to toggle it so that I get the exact value. And so then I'm going to hopefully, so now I'm going to graph this. So this is the slope. So y equals negative 20 over 7. Oh, and then there's an x. And then we already know that the intercept is 2. So let's see if I did a good job. Woohoo! Go me. I'm a little off. So why would I be a little off, do we think? I feel like I'm a little off. It might have to do with rounding of the points here. Because I only have one decimal value. Yeah. Thank you, Tom. There's Tom. Yeah. Tom's answering my question. So again, that is a way to help students try to understand, what do you mean when we're doing transformations of functions? Well, it's very similar to transformations of geometric objects. A lot of the same rules apply. So now I'm looking at my time, and I want to make sure I have time for this. But you could continue this with lots of different types. You could do reflect over the y. What would the equation then be if you reflected over the y? And what did we learn about the y? Well, the points would be different, right? They would be, and I can pull up another. Oh, we'll let it be red this time. So I could pull up another one, and we knew that we could do the same points here, and that the y was the one that changed this time. So if my original point's negative 0.70, well, that would be the same. That doesn't make sense. Did I do that wrong? Y coordinate is now its inverse. No, that makes sense. That makes sense, because this is now, I was thinking, well, that doesn't make any sense. This point right here then becomes becomes the intersection. I was confusing myself. Yeah. So you could do the same thing. You could have them plot the points, what they know happens to the points. Pick points, plot the reflection of the points, because that's related directly to their geometric understanding, and then use those points to then figure out the equation, and then have them compare these equations and what's similar, what's different, and how could that help you when you're working with your transformations. So then we're going to extend it just a little bit more. And so now I'm going to pull up a second graph here. And I'm going to show you how to use sliders to help students, again, still make those connections, but have an understanding of what's happening. So I'm going to this time, so here's my graph, and let's make sure we change some things here. I like to do decimals mainly because it helps me. And let's leave it at 2, because sometimes the rounding does come into play, like as far as precision. Oh, and I forgot to show you this. I meant to. So we use a little table here, right, to do our orange points. What you could do after you are done, and now you have your 2 equations, you'll notice when you hit the equation thing that you get this little table icon. And if I click that, that actually gives me a table of values for that function. And it's automated to be between -5 and 5, but you can add any point in here. So then if I did the same thing with the orange line, they end up right next to each other, and I can really start comparing my points. And so -1, comparing them and trying to get some relationships and understanding that way too. So you can pull up the table after they have the equation ready done, and do some more trying to understand what's happening when you reflect. So now let's go into this one. So one of the things when I work with transformations in algebra is I like to start with the parent function. So the one that you're basically transforming. The parent function is the standard. So we're going to just do the quadratic right now. So I'm going to put the parent function in green, and that's never going to change. Here is my parent function of a quadratic. All right, so we could talk about what are some of the key things here. So when you click it again, key point, so there's only one key point here, 0, 0, and that is my minimum, right? And now we're going to focus on how do we understand what is happening when we have function transformations, or we have an equation that's not the parent function. How's the parent function transformed? So what I'm going to do instead of, let's change yellow. Yellow's a yucky color. We're going to use purple. So now I'm going to use the standard form of this. And instead of using new numbers, actually, let's go back. I could do something very simple like, let's put a number in front of x. So if I put a number in front of x squared, and I just put the 1, I put a 2, how is that going to change the parent function, right? So what is that value, that coefficient that is with the x squared, doing to my parent function? How is it transforming my parent's function? And so when I hit this, this is one way to start having students think about it. What do they notice? So if you were a student, think back to geometric transformations. We didn't talk about this one very much, but what happened to the parent function, the green one, when I put that coefficient 2 with the x squared? So what happened? It makes it skinnier. So if I were to think back to my transformations of geometry, which transformation changed the size of my shape? Narrower or skinnier? So which transformation? Was it a translation? Was it a reflection? Was it a rotation? It's a dilation. And so what if in just one quick little example, I have shown that this value that's with the x squared is going to dilate my function. So if they're looking at it and they're like, well, a 2 made it smaller, which seems counterintuitive, would a smaller number, so a number, say, less than 1, because remember, this is a 1 right here. If a number less than 1, what do we think? We can make a conjecture. If we use a number smaller than 1, what might happen? And have them guess. Like, this is a great way for them to understand. Like, they understand dilations change the size, so we're getting skinnier. So if I want it to make it fatter, maybe it's a smaller number. And you can do this so quickly with dynamic geometry or dynamic math. So let's do 0.5, and it should be bigger. And it is. Woohoo, we've already figured this out. So right away, I already know that the number that is the coefficient with the x squared is changing the width of my parabola. All right. So now let's explore some other things. So you could continue to do this one number at a time, having conjectures, testing it out. What if I wanted my parabola to flip over? And what's a flip? So now we go back to our geometry. A flip, or as a reflection, what would make this flip over? Well, very good, Amy. When we flipped, it became the inverse, right? So an inverse would mean the negative of this x, whatever it might be. So I'm going to this time put a negative value, make that x squared be the inverse. And so now what I think is going to happen to my parent function is that it's going to flip. And it did. All right. So then you could say, okay, what if you want it to flip, but be skinnier? Can you give me a value that would make that happen? So lots of connections to that reflection that was the inverse of the x, and then the dilation that made it change its size. So if I want it to be flipped and skinnier, I'm going to use a number larger, a digit larger than 1. So let's try 3 this time. And it's much skinnier, right? So we've done all of this. So that's one way to do it, is to actually use numbers, because it's so fast in dynamic math that you can do that. But I want to end with showing you another way that I love, is to actually use your standard notation. So the standard form of a parabola is ax squared plus bx plus c, right? So I'm going to put that in, and I want you to notice what happens. If you use variables or letters instead of numbers, you create sliders. Now, one thing you do have to know is this, because Classpad recognizes multi-character variables, if I don't put the multiplication symbol in here, it thinks this is the variable ax. So I'm going to make sure that I put my multiplication in here. All right, so then and so notice, I haven't finished my equation yet, but notice that that variable is now interpreted as a slider. And so now I'm going to continue. So I'm going to do b times x plus c. And so you'll notice each one of those now has a slider. And so sliders are a really nice way to explore very quickly what's happening and kind of make some connections. So one thing you want to do, so here's the sliders. The default of a slider is to always default to the number 1. And you can change the range. It again, defaults -10 to 10. I can leave it at that, but since my window right now is only 6, maybe I want to just do -6 to 6. Doesn't really matter. So we're just doing it that way. I'll leave the other ones as they are, just because I'm running out of time here. And then step. So step, it defaults, if I start moving this, and it defaults, it does 1/10 at a time, which is kind of slow. So I don't usually like that. So either do, 0.5, or if you're really just beginning, a 1 is a really nice one because you kind of are just trying to use this as a way for students to see what's happening. So 1 is a nice whole number that makes it work really nicely. So now you could, what did we already figure out about A? We figured out that if it's has a digit greater than 1, that the parabola is going to be skinnier. And if it has a digit that's less than 1, it's going to be wider. And then if it's a positive, actually, if it's the inverse of the original, the parent here is positive. So if I do a negative, I'm going to flip it over. So those are the things we've already learned. But now you could explore that with your slider. And I'm just going to hit the, I like to use the animation because then you see it happening. So let's just hit this animation. You can see it changing as it goes. And this makes sense. So now it's 1 and flipping over. So we can watch what's happening. So then we're going to stop. Whoops. I don't know why it did that. Oh, can someone explain why it did that? It's a line. Uh-oh. Why did it do that? This is a great actually exploration for students. Like, why all of a sudden is my parabola not a parabola anymore? And it's because A is 0, which means there is no x squared. So it's a great kind of revelation for students. Oh, we don't have to have. And now it's just a linear. So that makes sense. So let's put it back. So now notice that this parent function and the purple function are not lined up. And A is 1, which is what it is in the parent function. So that means one of these, the B or the C, is impacting where the second function is. So now let's kind of look at what happened. The purple function is the same size as the parent, but it is to the left and up. So what does that mean happened to it? If I can see that it's to the left and up, what happened to it? What transformation occurred? Hopefully, I'm running out of time, so I'm just going to answer myself. It would be a translation, right? It slid to the left and it slid up, right? So what coefficient here is impacting that? So now we can explore these. So let's see what B does. So, and again, I like to hit the animation so I can see it. So B seems to be moving it in an interesting direction, kind of around. So B's kind of making it move around that point there. So, okay, so that's making it kind of go left or right. And let's see what C is doing. And C is, if you look at C is going up when it's positive and it's making the parabola go down when it's negative. So that's sort of my up-down movement. So maybe it's a combination of B and C together, and that's what we're going to figure out. But that means I'm doing some type of translation, and B and C are controlling that up, down, sideways kind of movement. So this is what you're trying to connect back to from geometry, is having them say, oh, that looks like a translation. How am I going to figure that out? And you can go back up to these functions and notice that there's those tables again, and compare the table results once you kind of match up these corresponding points and see how that connects, how these two connect to each other. How did it transform the parent function? And how can you tell just from looking at a function what transformations occurred? So that's sort of where I was going, trying to connect prior knowledge. And so I'm going to end right now and just see if there's any questions from anyone.
No, I don't see any.
Doesn't look like any. So I'm going to switch my share, I think, if I can figure out how to do that, back to my slideshow. And there we go. And I'll do this slide and then Amy, you do the rest.
Sounds good.
Okay, and I really appreciate you guys coming and spending time with us. Just trying to give you guys ideas on how to use visualization and prior knowledge to really help students. And these are great tools to use if you're teaching remotely. We have a lot of upcoming webinars coming. We've got them scheduled through April. So as you can see, we have some calculator ones. So those are February 17th and March 17th. Those are function transformations. So we're doing kind of a similar thing, but with the graphing calculator technology. And then on the 17th, we are doing some prep for the standardized testing on the ACT using your calculator. And then there's Classpad. There's some more Classpad ones. So we're going to do some more geometry, congruency, and similarity, and then some probability simulations on the 7th. And then we also have, if you ever want to look at the webinars and register, here are the links to those sites. So here's where you can find the specific Classpad webinars, and then also the Casio education webinars for the calculators. And on these pages, there are also our partner webinars, which Amy's going to talk about real quick.
Yes, so this series we've partnered with Todos. So all the speakers are members of Todos, and we are looking at distance learning and access because we know that everyone is still going through either completely remote or a hybrid version of teaching. So this series does start next Wednesday, and we have 2 in February and 2 in March on kind of the same days. They start at the same time, so it'll start at 7 Eastern as well. So if you'd like or are interested in joining us on those and joining these discussions, you can check out who the speakers are on the registration pages at the bottom there. So thank you guys so much for joining us tonight. For those of you that joined us live or through Facebook, if you are interested in learning more about our technology, please follow us on social media. We'll be posting about future webinars as well as other information. And if you need a certificate of attendance, please you can reply back to the follow-up email that we'll send out tomorrow, as this webinar has been recorded and will be posted on our YouTube channel.
And additionally, if any of you are attending the NCTM Virtual 21 conference, we are there every day, Amy and I, from 10 to 3 on the website, and we are happy to do some live demos if you have any additional questions. So stop in if you are attending that. And that's it. So good night. Thank you.
Thank you, guys. Good night.